Now we're going to analyse the motion of the car that we've seen before, but we're going to do it using differentiation instead of doing it just graphically. Now previously we told you that we'd made the first motion of the car such that the displacement was equal to t squared, the elapsed time squared. And the reason we did that was because we knew what was coming next. So now we know that when we differentiate x equals t squared, we get dx by dt equal to 2t. And dx by dt is equal to the velocity. So the velocity is equal to the elapsed time, whatever that might be, multiplied by 2. And so a couple of examples of that at this point here, when t equals 2, the velocity is 4. And at this point here, when t equals 4, the velocity is 8. What next? Well, now we know that the equation of that line is that the velocity is equal to 2t, we can find something out about the acceleration by differentiating it again. And then we get dv by dt is equal to 2. The linear term in t differentiates and the t seems to vanish magically and we're left with the number 2 here. And what that tells us is that there is no time dependence here. The acceleration is constant and has a value of 2, which we knew before. So that all works out. So that's the first part of the motion. What about the second part? Well, if we're going to do the same thing for the second part, we need an equation for the displacement of the second part. And here it is. And you've not seen that equation before, and at first sight it might look a bit weird. But what we know is that the velocity in the second part of the motion is 8, and that means that the displacement in the second part of the motion is going to have something to do with 8, the velocity, multiplied by the elapsed time. Now it's the elapsed time in the second part of the motion that counts for this, and this second part of the motion started at t equals 4. So the elapsed time of the second part is 4 seconds less than whatever it says on the t-axis here. So for example, when t equals 7, it's actually been doing 3 seconds worth of the second part of the motion. So that's what this little bracket is for. And the bit on the end, what's that doing? Well, at the start of the second part of the motion, it had already travelled 16 meters. So you've got a plus 16 on the end. Let's simplify that a bit algebraically. We can just expand the bracket, which becomes 8t minus 32. And then we've got the plus 16, so it becomes that expression shown. And when we differentiate that, dx by dt is equal to 8. Once again, we've got a linear term in t, and when we differentiate, the t disappears and we're left with the bit in front of the t, and the constant term disappears altogether because that has no rate of change. It's not changing at all, it's just constant. So there we have dx by dt equal to 8, but we knew that anyway, because what that's telling us is that the velocity in the second part of the motion is 8.